Hello and welcome. Today we're going to be looking at the mechanisms for directional hearing in fish. This is a research paper that we've all been reading. So the topic is about directional hearing in Dentinella cerebrum, and it presents a key question on how these fish determine sound direction using pressure and particle motion cues. So the hypothesis it presents is that the fish combine pressure and particle motion for determining sound direction. It challenges the traditional methods of ITD and ILD, which are used in terrestrial organisms. It introduced in Shujev's model, which compares phase between the pressure and particle motion for directionality. Some physical principles it uses is the inner ear separation is smaller than sound wavelengths. The acoustic impedance between water and tissue is similar, so there's reduction and attenuation. We're near a monopole source, this end polarity bit, where there's a 180-degree ambiguity, which can be resolved by Shujev's model by using pressure as a reference source instead of particle motion. Some limitations in the current theory. So M polarity alone was insufficient to explain the directional hearing because it lacks directional bias when only particle motion is present, and this was seen in the experiments. And then also ITD and ILD mechanisms are not sensitive enough with the small ear separation within this fish based off the wavelength of the source. So why this is important, the advancements we're making, it explains their directional hearing using phase comparison, and because this fish shares many organs with other fish, it could explain directional hearing in those fish as well. And it just advances our understanding beyond the simple models of ITD and ILD models for aquatic animals. Here's the experimental setup seen on the right here. We have an inner tank surrounded by an outer tank with hidden speakers, black and white walls to keep the fish oriented. It was found that they prefer a certain direction based off the color. We measured the responses with camera above and measured startled reactions, sharp swimming or bending. And then the parameters we looked at, we varied the pressure using varied the pressure and the x acceleration. We kept the y acceleration 0 using a 167 dB waveform. We had different configurations, pressure, x motion, combining them. And the experiments found that both pressure and motion cues are needed for directional responses. So it's limited us to 3 potential methods for directional hearing. And the final one that we came upon was Shujev's model because of the organs the fish itself contained. Here's the mathematical models that we use. We're going to use particle velocity later in designing our own system to determine a distance by looking at phase. And we're assuming the sound comes from monopole source. We're like in the far field, we're not near the walls. The fish itself was not. And we measured particle acceleration using accelerometers. To replicate the system, we would need a hydrophone for pressure signals, a particle motion sensor for motion in 3 axes, signal processor to compare the phase between the two so that we can determine the actual direction. We need a protective housing, some output display. It needs to be able to handle varying depths. We're assuming we're in the far field. We have constant medium properties, density and speed of sound are not changing. We have accurate phase measurement. To measure the distance, this is where we would use the phase differences between particle motion and pressure signals. And we could use this equation here by knowing the frequency of the source and the medium we are in. We could determine R because we are measuring the phase difference, measuring the phase. Again, we're assuming we're in the far field. We have homogeneous medium properties, and these are accurate phase measurements. Thank you for listening to my presentation, and have a great day.